In this lecture, we will introduce basic concepts of building physics and heat transfer, and we will describe energy balance of the building. To understand the heat flow across the building envelope, the understanding of basic heat transfer mechanism is required. The energy moves from a hotter to a colder object by three mechanisms. Conduction, when two objects are in physical contact. Convection, when heat is carried out by a moving fluid, for example, water or air. Radiation, when electromagnetic waves or radiation carry heat from one object to another. In the conduction, when a solid body is heated, the heat is transmitted from one end to the other. The atoms of the warmer part of the body transmit their greater thermal agitation to those adjacent to them, and the body progressively increases its temperature. When the body is heated continuously from one part and has reached the steady state, the temperature gradient through its linear as in the case of a homogeneous wall. The thermal flux Qc, which is the amount of heat transferred per unit of time by conduction through a homogeneous wall of area of capital S and of thickness S, is calculated by this formula, where Qc is the thermal flux in watt. Ts1 and Ts2 are the temperatures of the phases 1 and 2 in Kelvin. Rs equal to S divided by lambda is the thermal resistance of the material constituting the wall in square meters Kelvin per watt. Capital S is the area of wall in square meters. Lambda is the thermal conductivity of materials in watt per meter Kelvin. Small s is the thickness of the plate or wall in meters. The thermal conductivity is a specific property of each material, and it defines the higher or lesser ability to transmit the vibration of an atom to the adjacent ones and so to conduct the heat inside from one point to another. It is dependent on the temperature, density, and moisture content of the material. Typically, low density materials such as polystyrene also have low thermal conductivity, while those with high density materials such as concrete have elevated thermal conductivity. The second mechanism is convection. When a fluid flows around a warmer solid body, the thermal agitation of the solid body is transmitted to the molecules of the fluid, which increases their speed and the fluid is heated. In this case, since the portion of the warmer fluid that is in contact with the solid has a lower density than that of rest of the fluid, it tends to move upwards. On the contrary, if the fluid is warmer than the solid body, the part in contact loses heat and cools down. Its density decreases and it tends to move downwards. The thermal flux Q conv due to convection is calculated by this formula, where Hc is the convection heat transfer coefficient in watt on square meters Kelvin. Capital S is the area of the wall in square meters. Ts and Tf are respectively the surface temperatures of the solid body and that of the fluid in Kelvin. The third mechanism is radiation. Electromagnetic radiation can also be seen as a group of photons whose associated energy is a function of the wavelength traveling in the space. When a photon hits an atom, an increased thermal agitation is generated. When the temperature of a body is increased, the amount of radiant energy, QR, can be calculated according to the Boltzmann law, where QR is the radiant heat flux in watt, epsilon is the emissivity of the surface, which is the ratio of the radiant flux emitted from the real body and that emitted from the black body at the same temperature. Sigma is the Stefan Boltzmann constant in watt per square meter and fourth power of Kelvin. S is the area of emitting surface in square meters. T is the absolute temperature of the emitting surface in Kelvin. A body not only emits but also receives radiant heat, being surrounded by other bodies. What matters is the net balance of energy, which is the difference between the radiant heat emitted and the radiant heat received. This balance depends also on their positions, which determine the reciprocal apparent surfaces. The greater the apparent surface, the greater the amount of radiant energy the body receives. To quantify the phenomena, the view factor FPI, called the form or shift factor, is used, indicating the proportion of the radiation which leaves a person P that strikes surface I. There are four ways in which electromagnetic radiation interacts with the metals: transmission, reflection, absorption, and emission. Transmission takes place when radiation passes through a material. Reflection is when it is reflected by the surface. Absorption is when radiation is absorbed and converted into sensible heat. Emission is when the material emits radiation from its surface. It is always has this relationship where tau, rho, and alpha are respectively the transmission, reflection, and absorption coefficients. For most of the materials commonly used in construction, the emission is equal to absorption. When the surface of a building are hit by solar radiation, the external surface temperature increases depending upon the incident solar radiation and the absorbance of the surface. This can be taken into account by increasing the external air temperature to an appropriate value to obtain the same effect. This increased value is called soil air temperature. The flow transmitted through a building surface due to soil air temperature QSA can be calculated with this formula, where Q is the heat flow due to actual external air temperature in watt. Alpha is the absorption coefficient of the surface. IS is the total solar radiation incident on the surface in watt. A building considered as a thermodynamic system is an open system whose boundary, which is the building envelope, separates internal phenomena from external one and is crossed by fluxes of energy and matter. These fluxes vary continuously over time. Therefore, the building is a dynamic system, not just because the light illuminates it in a different way depending on the location, season, and time, but also because there is not a single molecule of its structure that does not continuously change the thermodynamic parameters that affect comfort and energy demand. The water analogy is useful to understand the energy balance of a building. If we imagine a bucket with holes in the bottom and the sides, we know that if we fill it with water and we want to maintain a certain level, we need to provide as much water as it loses. In the same way, to maintain a certain temperature inside a building in a cool period, since there are heat losses, we must provide as much heat as it loses. And this is done with the heating system. The holes of a building in winter are the transmission heat losses through the envelope, and those due to air filtration and ventilation. Actually, there are not only losses in the relationship between the building and the environment, there are also solar gains, as if the bucket was placed outside, where the rain helps to fill it. To these gains, the internal gains, the heat produced by the occupants, lights, and the equipment must be added. In summer, things go in a similar but opposite way, as in a boat with leaks in the hull. To keep the boat floating, water must be pumped out. This corresponds to the building in the summer when the heat penetrates and you have to pull it out with air conditioning. The penetration takes place through walls, roof, and windows, and through infiltration and ventilation. In this case, there are also solar gains, but they now do not help. On the contrary, they tend to increase the temperature of the environment. In the same way that rain would fill the boat faster, raising the water level. The energy balance of a building in watts at time t can be solved according to this equation, where Q is the heat flow through the opaque roof, walls, floors, and glazed windows envelope components. QZL are the solar heat gains through the windows. QV is the ventilation heat flow. QI are the internal heat gains due to the people, domestic appliances, and the equipment. QM is the sensible heat demand compensated by the heating or cooling system. In general, the energy balance of building envelope regards the thermal energy flows required to maintain the desired condition of temperature and humidity in rooms. The architectural choices are crucial for the part of the balance that covers the sensible heat. Latent heat is, however, the heat released or absorbed when the water content, for example, in the air changes state. The balance of the latent heat, in fact, depends only on internal sources like people, plants, and kitchen, and on outdoor air conditions. Thus, the envelope characteristics have no influence on it. While designing energy efficient buildings, energy managers must have a good knowledge of heat transfer and energy balance of buildings for achieving high energy performances and occupants' comfort.